Hello, grade 12s. Welcome to the Pedagogical Science Institute for the people. And my name is Karao Seniga. And in today's lesson, we'll be focusing on physical science, the physics part, mechanics, and according to the examination guideline, we'll be focusing on paper 1, which focuses on physics, the content, which is mechanics, and it carries 65 marks. Or we'll be looking at Newton's laws and application. In this session, we will be examining different types of forces, review and apply Newton's laws of motion, and lastly we will do a review of Newton's law and Newton's law of gravitation. Now, the nature of forces. Forces can be divided into two categories, contact forces and non-contact forces. The following are non-contact forces: gravitational forces between a planet and an object on the planet. And we have the electrostatic forces, and these forces can be found between charged objects. And lastly, we have the magnetic forces, which are found between magnets. Coming on to contact forces, examples of contact forces include normal force, frictional force, tensional force, and applied forces. And these ones, we will look them later on when we come to Newton's second law, when we come to application of Newton's second law. Now, Newton's first law. It states that a body will remain in its state of rest or uniform motion in a straight line unless acted upon by an external resultant force. Newton's first law states that a body will remain in its state of rest or uniform motion in a straight line unless acted upon by an external resultant force. In other words, unless a resultant force acts on an object, that object will remain in its state of rest, or if it were moving, it will continue moving at a constant velocity in a straight line. Let's take a look at this. Let's say we have a box, and this box is sitting on top of a table. This box will remain in its state of rest or uniform motion unless acted upon an external resultant force, meaning that it will not move unless someone comes and pushes this box, and the person that will be pushing this box will be referred to as that external resultant force, hence the box will move. If there's no one who's coming to push this box, that box will not move, hence it will remain in its state of rest or uniform motion. Another example, a passenger sitting in a vehicle that is moving at a constant velocity will be thrown forward if the vehicle suddenly had a brake. This is because the passenger wishes to continue moving at that constant velocity in a straight line. Okay, now coming on to another term that is related to Newton's first law, which is called inertia. Inertia is referred to as the property of matter which maintains an object state of rest or uniform motion in a straight line. Inertia can also be defined as the resistance of an object to change its state of motion, or we can say that is the simplified definition of inertia, which is the resistance of an object to change its state of rest. Now, moving on to Newton's second law. It states that when a resultant force acts on an object, it causes that object to accelerate in the direction of the resultant force, whereby this acceleration is directly proportional to the resultant force and inversely proportional to the mass. Now, looking back at that example of a box on a table, I want us to take a look at this box and apply this statement on it, whereby this acceleration is directly proportional to resultant force. This simply means that the more force you put on pushing the box, it's the more you increase the acceleration of the box, meaning that the stronger the force applied, the faster the acceleration will be, or the faster the box will move. Hence, this acceleration is directly proportional to the resultant force. And by inversely proportional to the mass of the object, this simply means that the heavier the box, the slower the acceleration will be. Meaning, if the box is more heavy, the box is most likely to accelerate in a slower pace. Now, Newton's second law in terms of equations. It can be mathematically defined as F net is equals to ma, whereby a represents the acceleration and m the mass of the object. F net, all the forces that are acting on that particular object. Now, Newton's second law types of questions. These are type of questions that are most likely to be asked when dealing with Newton's second law. Newton's second law questions come in many different forms, and the forms are listed below. Please take note of the following points when solving Newton's second law questions. The first point is that it helps to draw a force diagram. It helps to draw a force diagram labeling all the forces acting on the object, even if the question does not require you to do that. Another point is that according to Newton's second law, F net is equal to ma, but also mathematically F net is equal to algebraic sum of all forces acting on an object. And in most cases, it will need to combine those forces, those two statements, to solve a given problem. Last point, in case of more than one object within the same question, it is advisable to let the examiner know which object you are considering in your calculation. For example, if you are given a problem where we have two boxes that are held together by a string, let's say the boxes are identified with two different masses. Let's say we have a 1 kg mass and a 2 kg mass. When you're calculating, let's say maybe the acceleration or the tension, you are required to indicate that in this F net is for a specific box, the 2 kg block, and this F net is for a specific block, the 1 kg block. Hence, you are advisable to let the examiner know which object you are considering in your calculations. Following are the types of questions you expect when dealing with Newton's second law. A question that is based on a horizontal plane, where one force is acting on an object, and the force applied is equal to F and the force applied is F is equal to F net is equal to ma, whereby we have only one force that is acting on this object, which is referred to as the force applied. This force here, it will be the only force that is acting on this object. But in this case, this is not the only force that is acting on this object, simply because you have the coefficient of kinetic friction. And once you see the coefficient of kinetic friction, this simply indicates that we have a friction force, not necessarily friction force, but a kinetic friction force acting on this object. We have the kinetic friction force acting on that object, simply because you are given the coefficient of kinetic friction. Now, another type of question to look at is the one that consists of one force acting at an angle of a horizontal, at an angle theta to the horizontal, whereby the horizontal component of force Fh is equal to F net is equal to F cos theta. Simply meaning that when we are dealing with this kind of forces, which has an angle theta to the horizontal, before you do all the calculations, you must firstly resolve this force here, this force applied to the horizontal. You must resolve it so that it can be on the horizontal plane, simply because when coming to Newton's second law, we only calculate forces that are on the horizontal plane, not forces that are on the vertical plane. Hence, you must be able to resolve this, And here is the equation for you to do that. F8 is equals to F net, which is equals to F cos theta, whereby our theta will be 30 degrees and our F will be 50 newtons. Moving on, we have more than one forces acting on an object. Problems that are considered that are problems that have more than one force acting on them, whereby F net will be equals to MA and it will be equals to algebraic sum of all the forces acting in that horizontal plane. Example will be F net is equals to MA is equals to F plus into bracket minus the frictional force, we can say. Looking at diagram number 1, we have two forces. We can name this force A and force B. And in sorry about that. It must be force B, force B, force B, force B, force B. And in this case, force A and force B have the same magnitude. Force A is equals to 5 newtons, force B is equals to 5 newtons. And when coming to apply this equation here, the F net is equals to MA, which is equals to F minus the small f plus minus the small f. You can see that this box is at rest because of the force A is equals to force B, which means that they will cancel each other since the two forces are equal. Coming on now to the second diagram. The second diagram we have, let's label this as force A. We have force A here, we have force B, which is 39 newtons, and we have force C, which is 63 newtons. In this case, you will need to add force A plus force B. Let me get that right. You will need to add force A plus force B since they are going in the same direction. And then 24 newtons plus 39 newtons will simply give you 63 newtons. After you added force A plus force B, which will be the resultant force of the force A and force B, you will need to, let's say, F net for this is the F net for force A and for force B. You will need to minus force C since it is going in the opposite direction as the two forces, and therefore F net minus FC will simply give us zeros because 24 newtons plus 30 newtons plus 39 newtons is 63 newtons, and for C is also 63 newtons, meaning these two objects, the horse and the man, are at rest. They are not moving. There is no acceleration between the two objects. They are at rest. Oh, and it's always advisable to consider the direction to the right as positive and to the left as negative. Hence, we minus for C here since it was going in the opposite direction. But it's not always the case that you must consider the right direction as positive. It's up to you. You can always consider the right as negative and the left as positive. It's up to you. Coming on now to more than one force acting within an object at an angle theta to the horizontal. In this case, F net is equals to MA is equals to algebraic sum of all forces acting in the horizontal plane. And like I said in the previous slide, when you have a force like force F here that is applied at an angle theta, you will need to resolve that force first before doing all your calculations. After you have done that, hence you now can be able to add all algebraic sum of all the forces acting on that horizontal plane. that's when you will start now to add all the algebraic sums acting on this force. And we can see here, if we were required to draw a free body diagram, we'll have our normal force here, we'll have our weight, we'll have our friction if it's there, and we will have our force F here, which will need to be applied, which will need to be resolved, which will need to be resolved in the horizontal plane. We have our friction here, we have our weight. Now after resolving this force here, that's when now you can add up all the sums of the forces that are acting on that particular object. You can now add all the forces that are acting on that particular object, whereby F net is equal to MA, which is equal to algebraic sums of all forces acting in the horizontal plane. Moving on to inclined plane. On a frictionless plane, the object rolls down due to the weight parallel. In this case, we have two types of the weight component. We have the mg cos theta and we have the mg sin theta, whereby the mg sin theta is refers to as the weight parallel, which is always parallel to the surface, and the mg cos theta, which is the weight perpendicular, which is always perpendicular to the surface, making an angle of 90 degrees. Making an angle of 90 degrees. Making an angle of 90 degrees. Always perpendicular to the surface. Okay, moving on. If there is an upward force or friction or a tension by a rope, the F net will be equal to MA, which will be equal to algebraic sum of the forces acting on that plane. But in this case, when you are calculating your F net, you will also need to include the weight which you will also need to include the weight perpendicular, the weight parallel, as it is acting as one of the forces that acts on that object. You will need to resolve the weight to the horizontal, and it will be weight perpendicular is equals to mg sin theta. That will act as one of your forces since it is on the horizontal plane. Coming now to Newton's third law, it states that when body A exerts a force on body B exerts an equal and opposite force on body A. When body A exerts a force on body B will exert an equal and opposite force on body A. Looking at this equation here, looking at this diagram here, this person is applying a certain amount of force on the wall, and the wall in this case is not moving. Because of why? Newton said that the law is also applying the same force as the person, but in the opposite direction, simply meaning that those two forces will cancel each other, hence the wall will not move. Please note the following regarding Newton's third law. In every interaction, there is a pair of force acting on the two interacting objects. The size of the forces of the first object equals the size of the force of the second object. Hence, there is no movement between the wall and the person. The direction of the force of the first object is opposite the direction of the force on the second object. Lastly, the forces are referred to as action-reaction pairs. Oh, these forces are acting on separate objects. Okay. That was all you need to know about Newton's third law, the action reaction. Now coming on to Newton's law of gravitation. The gravitational attraction on on an object, which is the weight, depends on the mass of the object. Simply meaning that the weight is equal to mg multiplied by the gravitational acceleration. No, man, not mg, m multiplied by the gravitational acceleration. Therefore, moving on, the mass of the attracting object affects the force of attraction. Therefore, the gravitational force is directly proportional to each mass. The mass of the attracting object attracts the force of attraction. Therefore, the gravitational force is directly proportional to each mass, meaning that if we increase the gravitational force, obviously the mass of each object will also be increased, hence directly proportional. As you can see here, gravitational force directly proportional to mass 1 and directly proportional to mass 2. Therefore, the gravitational force is directly proportional to mass 1 and mass 2, meaning when we increase the other one, the other one will also be increased. Another factor affecting the force is the distance r between the object. The distance r between the object. The force of attraction is inversely proportional to the square root of the distance. This simply means that when we increase the force of attraction, we will definitely be increasing the square of the distance. The higher the force of attraction becomes, the lower the square, the shorter the distance will be. Hence, F is inversely proportional to the square distance. Equation wise, F is equal to 1 over r squared. Therefore, F is equal to mass 1 is equal to mass 1 multiplied by mass 2 divided by the square of the distance. If we introduce a proportional constant G, which will be F, our equation will then be G is equal to it will be F is equal to G multiplied by mass 1 multiplied by 2, all divided by the square of the distance. Oh, and we are given the value of the G, which is the proportionality constant. Now, Newton's third law, Newton's law of gravitation state that every body attracts every other body in the universe with a force that is directly proportional to the product of the masses of the two bodies and inversely proportional to the square of the distance between them. Hence, we have this general formula here. F is equals to G multiplied by mass 1 multiplied by mass 2, all divided by the square of the distance between them. Gravitational acceleration, which acts independently of the mass of the object. An object mass experiences a force of attraction by the earth and this is the weight of the object mg. The same force represents the force of the gravitational attraction the object in the earth, and we know that our gravitational acceleration is equals to 9,8 meters per second squared. That is our gravitational acceleration. Now, our equation for the gravitational acceleration is derived from the general formula. Hence, we have G is equals to capital G multiplied by M all divided by R squared. That is our equation for the gravitational acceleration, which is derived from the general equation of the Newton's gravitational law. From the equation above, it is clear that the gravitational acceleration is independent of the mass of the object, but dependent on the mass of the Earth. or planet. Okay, now we are coming to the application of Newton's second law. Okay, Newton's laws checklist. Make sure you can state all the Newton's law. You can draw free body diagram and force diagrams. Know the difference between the kinetic and static friction. Can calculate friction, can calculate resultant force. Know how to use all the equations. Now coming to exam questions. Question 1. In the diagram below, a 1 kg mass on a rough horizontal surface is joined to a 2 kg mass by a light intangible string running over a frictionless pulley, meaning that there is no friction. There is no friction on the 2 kg pulley, on the 2 kg mass. The coefficient of kinetic friction between the 1 kg The coefficient of kinetic friction between the 1 kg mass and the surface is 0,3. It's 0,13. Once we hear the word coefficient of kinetic friction, this simply tells us that we have the kinetic friction force acting on that object. Okay, question 1.1 requires us to state Newton's second law in words. Newton's second law of motion in words. And I'm not going to write it for you, but I'm going to state it for you. And we know from this equation like I said, we know from this equation that when a resultant force acts on an object, the object will accelerate in the direction of the net force, and that the acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Okay, let me state it again. Newton's second law of motion in weight states that when a resultant force acts on an object, the object will accelerate in the direction of the resultant force. The acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. Okay, now moving on to question 1.2. It requires us to calculate the magnitude of the kinetic frictional force acting on the 1 kg mass and calculate the acceleration of the 1 kg block of the 1 kg mass. Okay, firstly, let me read through the diagram so that we can be able to see what is happening while calculating. This is our diagram. Oh, it's on the table. The 2 kg block and the 1 kg block. Okay, and in this case it is advisable to draw your forces that are acting on this object. Firstly, we have the tension. This is our, let me get my marker. This here is our tension. We have our normal, we have our weight, and we were told that we have the coefficient of kinetic friction, meaning that we have our kinetic friction force. And in the 2 kg block, we only have the tension and the weight, which is going down. And in this case, the tension is positive, it's negative, and meaning that on the 1 kg block our tension will be negative. Okay, now coming on to question 1.2.1, it requires to calculate the kinetic friction force acting on the 1 kg block. Now, the equation for kinetic friction force is Fk is equals to mu k multiplied by normal. And we know that normal is equals to weight, which is equals to mg. That we know. Hence, we have the mu k, which is 0,113 that was given, and our our normal, which is mg. Firstly, our mass is 1 kg, and our gravitational force, which is 9,8. Therefore, our Fk is equals to 1,27 newtons. That's our kinetic friction force, which is 1,27 newtons. Now, looking at the acceleration of the 1 kg mass, for us to get the acceleration of the 1 kg mass, we must simultaneously find the F net of both the 1 kg mass and the 2 kg mass. Hence, we have the F net for the 2 kg mass, which is Fg minus Ft is equals to Ma. For the 2 kg mass, since we have only two forces that are acting on the object, which is the weight Fg minus the tension that is negative, is equals to Ma. And in this case, our weight is 2 multiplied by 9,8 minus the Ft, which is unknown, which is equals to 2A. Therefore, 19,6 Ft is equals to 2A, which will be our first equation. Now, like I said, we must simultaneously calculate this. We leave it here since we have equation 1, and we go for the 1 kg mass. And in this case, F net is equals to Ma, and our F net, also we have two forces that are acting on this object. We have the tension that is positive and the kinetic friction that is negative, which is equal to Ma. And the Ft again, it's unknown, and the kinetic friction force we calculated in the previous question, which is 1,27 newtons. Therefore, Ft minus 1,27 is equals to 1A, which will be our second equation. Now, for us to get the acceleration, we must add equation 1 with equation 2, then simultaneously calculate. Now, 19,6 minus Ft is equals to 2A, and Ft minus 1,27 is equals to 1A. Now, in the first equation, this is the first equation. In the first equation, the Ft is negative, and in the second equation, the Ft is positive, simply meaning that these two will cancel each other. Let me get my blue marker so that you can see clearly. These two will cancel each other, and we'll be left with 19,6 minus 1,27, which will simply give us 18,33. And then the two acceleration from the two equations, which is 2A and 1A, we add them, which will simply give us 3A. And to get the acceleration, you will need to divide both sides by 3. Both sides by 3. 3 will go out with 3, and we are left with A, whereby A will be equals to 6,11 meters per second squared. That will be our acceleration for the 1 kg mass, whereby acceleration is equals to 6,11 meters per second squared. Now, question 1.3. Let me redraw the diagram again. We have the 1 kg block. We have the 2 kg block on the table. 1, 2. Okay. The rough horizontal surface is now placed with a smooth frictionless surface. The 2 kg mass is again released and strikes the ground before the 1 kg mass reaches the end of the horizontal surface. Now, question 1.3 says, will the 1 kg mass move at a lower or higher or a zero acceleration? Briefly explain the answer by referring to Newton's laws of motion. Okay, in this case, I'm also going to give you the answer. I'm not going to write it down. In this case, the 1 kg will move at a zero acceleration. The 1 kg block will move at a zero acceleration. Simply because according to Newton's second law of motion, its acceleration will be zero, and according to Newton's first law of motion, it will continue to move in a constant velocity until it reaches the edge of the surface. Okay, let me repeat that again. Its acceleration will be zero, and according to Newton's second law of motion, its acceleration will be zero, and according to Newton's first law, it will continue to move at a constant velocity until it reaches the edge of the surface. Now, looking at question 2. Okay, a skier of a mass of 60 kg skies from rest down a slope inclined at an angle of 15 degrees. The length of the incline is 75 meters. He reaches the end of the incline at the velocity of 15 meters per second. A constant frictional force acts on the skier on his way down. Question 2.1 says that write down an expression for the magnitude of the normal force acting on the skier and then calculate its magnitude. As you can see, I've already done my calculations here. Okay, we know that normal force is equals to weight, which is equals to mg. That's done. And in this case, on an inclined plane, we have an angle of theta applied. Now, when we have an angle, obviously we must resolve this object to the horizontal. Hence, we have mg cos theta, whereby our cos theta will be cos 15 degrees. Therefore, normal is equals to fg is equals to mg cos theta, whereby our mass is 60 and our gravitational force is 9,8 multiplied by cos theta, which will give us 567,96 newtons, being our normal. Last question. It requires us to draw a free body diagram showing all forces acting on the sky as he skies down the slope. Okay, there are two different ways you can draw this free body diagram. Firstly, you can draw this diagram using the weight force, only the weight. Then secondly, you can use the weight component. Okay, let's look at whereby you use only weight. Okay, we will have our weight here in our kinetic friction, our normal. The second one will be whereby we have our two weight component, which will be weight perpendicular and weight parallel, and we'll have our normal and our kinetic friction. This is how you can draw a free body diagram in two different ways. Firstly, using the weight, and secondly, using the weight component. Okay, that brings us to the end of our questions. Thank you for attending this lesson. This is the end of our lesson for today. Thank you, everyone. Thank you.